Again, welcome to this OsmoDevCall about building wired RF test setups for cellular networks. Something that I've been doing for, well, probably almost as long as I've been hacking on OpenBSC and Osmocom and all the projects. So probably 15 years now or so. And for a lot of people who are more coming from the software side, there always seems to be a bit of, how can I say, a lack of understanding of the RF and the electronic side. After all, it's relatively simple if you know some basics, and the idea is to talk a bit about this in this presentation. So the assumption is that, well, you have some idea what a user equipment and what a base station is, and some idea, like some basic electrical know-how, but no specific RF knowledge, and nothing about designing coaxial antenna networks or things like that. What is this? Well, this is the overview, about what we will cover. So why would one want to do that? Some terminology, constraints, assumptions, a simple setup, some stuff about dBs and dBm and typical signal levels that we encounter, and we will look at the individual components that are used to build such RF networks, such as attenuators, duplexers, and so on, and how to put all of this together. So I have a couple of slides, and we may do more talking and explaining after the slides or during the slides. But let's first go through the slides, at least the initial ones. So the talk is about connecting the radio interface of cellular technology using a wired setup. So we have wireless technology, but we want to use wires. Why we will cover in the next slide. It just means that information that is normally sent over and signals that are normally sent over the air interface of a radio are communicated in coaxial wires and related devices rather than through the air interface. So why would one want to do that? Well, first of all, if you do all of this through coaxial cabling, you don't need a spectrum license since you don't broadcast, right? So only if you broadcast signals, you need a spectrum license from the regulatory authority. But if you're doing this all in a wired setup, there is no such need. So it reduces that requirement, which, depending on the jurisdiction, may be difficult to achieve. The other reason, maybe the more common reason, or one of the more common reasons, is that you have absolute signal levels or well-defined signal levels, which is useful for measurements. For example, if you want to test power control mechanism or measurement reports reported by your base station, there's no way how you can realistically test that, at least not in a quantitative way, unless you have defined an absolute signal levels. So if you apply a certain level to the coaxial wire and you know the loss of the coaxial wire, you know what will be received at the other end of the coaxial wire, and therefore it will be a stable signal. So you basically you have a defined electrical level, and you see whether your user equipment or base station reports the level that it's supposed to report in the measurement reports, and that way you can check that. Also, I mean, both on the receive side as well as on the transmit side, of course. You can also introduce defined attenuation, delay, noise, and all kinds of things if you wish to for test purposes. Or you can adjust parameters such as the attenuation on the fly to trigger cell reselection or handover in some kind of manual or automatic test setup. The other advantage is there is a chance to operate multiple setups in close proximity that shouldn't or don't interfere one another. At least if the screening of the devices is good enough, then you can have them in relatively close proximity, and your test setup A doesn't radiate into your test setup B, even though it might operate in the same spectrum, for example, if you have multiple such setups. So a bit of terminology. UE is the user equipment, meaning a cell phone, cellular modem, or something of that sort. I'm going to use BS here as base station term to basically avoid having to go through BTS node B, E node B, G node B, or whatever is the abbreviation or term of the respective cellular technology. All of the stuff that I'm going to present here is working on either of those, irrespective of the generation of cellular technology you're using within the constraints we will cover shortly. Uplink is by definition the direction from the user equipment to the network, and downlink vice versa. The easy way to remember that is to think of a classic cell tower with a high antenna. So if you're sending something up there, it's uplink, and if you're receiving it from the antenna down to you, it's downlink. So yeah, some assumptions or constraints. So I'm talking about 3GPP cellular systems here. That means 2G, 3G, 4G, 5G systems. Of course, a lot of this works with any kind of radio system, just as long as some parameters are similar. So for example, with Tetra, it would work just the same way. What I'm looking at here is FDD modes of these systems, meaning frequency division duplex, and not TDD systems, time division duplex. That's separate. So this entire presentation only covers FDD systems, where GSM is always FDD. There is no TDD mode for 3G. There is some TDD variant that almost nobody uses for 4G, 5G. Some people use TDD, but yeah, that's not covered here. And we're only looking at 50 ohm systems, as that's the only thing that covers or that matters in the context of cellular technology. So we assume all the devices have 50 ohms impedance and not looking at other things. Yeah, so let's look at the most simple setup that we can imagine. Imagine we have a user equipment implemented in an SDR, and SDRs have different RX and TX ports, unlike most other user equipment, which we will cover later. So this is what makes the setup particularly simple. So we have the user equipment with separate RX and TX ports, SMA connectors or whatever. And we have the E node B or the base station on the other end, which also has separate uplink, downlink, receive, and uplink, receive, and downlink transmit ports. So all that we need to do is to put attenuators in between for both the RX and the TX part, and connect them, of course, vice versa, so that the uplink transmit of the UE ends up in the uplink receive of the E node B, and the downlink transmit of the node B ends up in the downlink receiver of the user equipment. It's simple because, well, we have a user equipment that has separate ports, which is not a usual case. And it's also simple because we only have one base station and one user equipment. So it's really only about adding attenuation in between. And now we will talk about how to achieve that and how to compute what kind of attenuation we need in such a system. So let's get a step back, and what is the purpose really, and why can we not just connect with cables? Well, the signal needs to be attenuated to protect the receiver inputs from dangerous amounts of energy. So if you have a transmitter, most often that transmitter radiates a significantly higher amount of energy than your receiver expects, because there's a lot of loss in the radio interface over the air. But if you put coaxial cables, suddenly all of that loss is gone. So you need to artificially add the loss at the same level that the radio interface would have had if you went over antennas and then actually a radio interface. The other reason, I mean, so the minimum level of attenuation you need to do to protect the receiver, because the receiver is very sensitive and your transmitter often has tons of energy. But beyond the protection, it's also useful to be able to attenuate the signal more or less in order to simulate a UE close to the cell edge, meaning far away, which is a high loss, means high attenuation, or a UE that's close to the base station close to the cell center, which means you need less loss or less attenuation in your setup. And so if we look at this, we will deal a lot with two terms or acronyms. One is dB or decibel, and the other one is dBm, and it's important to not mix those two. Those are separate, well, not units, but things, let's say. So dB is a ratio of two values on a logarithmic scale. It's unitless. Think of it similar to percent, right? You cannot say I've earned 20%. Well, 20% of what? So it's always in relation to something. It's a relative measure or ratio that you always need to apply to some base value in order to have any meaning of how much it is actually talking about, and not just a ratio. So you would normally say things like this device, let's say it's an attenuator, it attenuates the signal by 30 dB. So you know what goes into the device is attenuated by 30 dB at the output, but you don't know anything about an actual signal level, because that, of course, depends on how much you put in, right? So you put something in, and whatever you put in is attenuated by 30 dB in this example. And that's contrary to the dBm, the decibel milliwatt, which quantifies an absolute RF signal value. So it's basically just a fancy way of saying so many watts or milliwatts or nanowatts, just in a different scale. So it's defined as in a way that 0 dBm equals 1 milliwatt, and then 3 dBm is 2 milliwatts, and so on. These are just some examples. The nice part about the dBm, expressing power in dBm and not in watts or milliwatts or nanowatts, is that it covers a useful range for RF signals in a very relatively low, small range. So if we were to do these calculations in watts, we would have to deal with, well, anything from, let's say, picowatts up to watts, and lots of orders of magnitude, whereas in dBm, in RF technology, what we're talking about is typically a range between minus 150 and plus 50 dBm. So the minus 150 is, we will not encounter in cellular systems, but let's say GPS, for example, it is something, the GPS signal can be as low as that. And plus 50 dBm is a rather strong transmitter, probably stronger than any cellular base station you will find. So that's sort of the kind of range in which we operate. And you would then say things like this transmitter transmits at 23 dBm, meaning basically it transmits at 23 dB above 0 dBm, which is 1 milliwatt, which if you translate it around, it would be, 200 milliwatts of power, if you want to express it in watts. One important rule of thumb, or was actually the rule of thumb, but some kind of thing to keep in mind, is that a step of 3 dB signifies a doubling in power. So if you talk about two signals that are, well, one signal is, let's say, 20 dBm and the other one is 23 dBm, then actually the 23 dBm signal has twice the power of the 20 dBm signal. And vice versa, if we talk about a 20 dBm signal and a 17 dBm signal, the 17 dBm signal has half the power of the 20 dBm signal. It's a bit unusual to wrap your head around that, but yeah, just keep in mind that we are not talking about linear scales here, but a highly logarithmic scale. And whatever, twice the dBm is not twice the power, but it's, you know, something completely else. So if we look at the kind of RF signal levels that we encounter in such systems, as I said, the scale goes about down to minus 150 dBm. Where would you encounter that? If you look at the data sheet of a GPS receiver, for example, it's not cellular, but still sort of something that you might have experience with. So a GPS receiver, a good one, can typically receive decode GPS signals down to minus 149 dBm. That's ridiculously low, and it's only possible due to the coding gain that's associated with the GPS signal. If you look at the actual sensitivity level means this is the minimum amount of signal received that I can still decode in a reasonable way. Then something like -109 dBm is something that you would find in a cellular base station, in a typical GSM base station, a commercial one. About -101 dBm is what the LTE specification says. A macro base station at 5 to 20 megahertz carriers bandwidth needs to have as a minimum sensitivity level. So basically, you cannot sell an LTE base station on the market because you wouldn't get CE certification if you don't meet at least the -101.5 dBm sensitivity. You can be better, meaning you can build a product that can still receive a signal at -105 dBm if you're good enough to do that. But if you cannot, if you can no longer decode a signal, I think at 95%. There's some additional rules given the spec. How well you need to receive it, how many bits you need to be able to decode, and so on. But if you cannot reach that target, you will not be conformant to the CE specification, and it means you cannot sell the product in the European and in many other markets. So on the positive scale, +6 to +16 dBm is the typical maximum power output you would get from a USRP B200, 210, something like that, or other device, software-defined radio devices that have an ADI transceiver. 23 dBm is the output power of a typical LTE user equipment, or also a Sysmo BTS 1002 or an IP Access Nano BTS if you work with 2G equipment. 23 dBm, which is, as you can see, 10 times as much power as 23 dBm, is the maximum transmit power of a GSM handset in the 850 or 900 megahertz band. Why is that relevant? Because if you have, let's say, some kind of cellular modem or phone or whatever device in your RF setup, even if you're working with 4G or 5G, the device can actually still operate most likely in 2G mode. There are very few user equipments that don't support the legacy technologies. And it means that if you get some kind of downlink leakage from a commercial radio cellular network into your RF test setup, the user equipment may start to register or may try to register on that signal and send RAT requests, and those RAT requests or other communication could actually be transmitted at 2 watts, even though in LTE or 5G mode, it cannot transmit more than 200 milliwatts. Once it switches to 2G mode, suddenly you're talking about a lot more transmit power, meaning that you need to make sure that basically even at that maximum transmit power of the user equipment, you do not damage any of the receivers or other equipment that you have hooked up in your wire test setup. In the higher bands, GSM only transmits at 30 dBm, which is only 1 watt, only in quotes. And if you look at the like commercial macro base stations, then we're talking about 10 to 20 watts as a typical transmit power. It could also be 40 watts or even more in some instances, but it's somewhere in that range. So we're talking about 43, 46, maybe 49 dBm, but that's already a super high output level. And our RF distribution network or wired setup basically needs to how can I say, adjust the levels to those expectations and within those ranges. All of this actually is not very different from doing a link budget or path loss calculation for a actual outdoor or indoor wireless deployment. There's entire books and whatnot and courses on that. Whether we do it over wire or over wireless is not so different, other than that the levels are higher or lower because, well, the cable has less losses than the air, the radio waves traversing through space. So basically, what do we have? We have to look at uplink and downlink separately. In both cases, one side transmits at a given transmit power, and the other end receives the signal at a received power. And the transmitter has a certain range of transmit power it can transmit. There's power control involved, but if we are talking about, let's say, protecting the receiver as a first goal, we always have to look at the maximum transmit power, for example, the 33 dBm in the GSM case that I just mentioned. And on the other end, we have a receiver, and now we need to check what is like a safe level of reception for that receiver. And then we compute the difference between the transmit power and the intended receive power, which leads us to the loss or the attenuation that we need to have in our path. And then that is what we need to implement in our network. So assuming the following example here, the user equipment transmits at 20 dBm, and the base station receiver has a reference sensitivity of minus 110 dBm. So if we subtract those two values or look at the difference, we see that the maximum possible path loss can be 130 dB. If we have more than 130 dB, then the link budget doesn't work anymore, and the receiver will no longer receive the user equipment. So that's the absolute maximum that we can have. So we have an upper bound for the amount of attenuation that we can put between the UE and the base station receiver. This example is only looking at the uplink side here. So, well, then, depending on how large your setup is and how high quality your components is, we subtract something. 5 dB is already a lot for cables, connectors, and so on to accumulate for all the losses that happen there. Then we add, let's say, at least 5 dB of margin because there's tolerances and whatnot involved. So let's say, okay, if we subtract those two values, we end up with 120 dB. And that's sort of the maximum amount of attenuation that we can put in between the UE and the base station to still make them work. The minimum attenuation that we need is defined by the highest reasonable signal level the receiver can process. That's something that's not easily found in a lot of documentation or data sheets. I'm not sure, for example, if, let's say, it's documented for SDRs, but a good rule of thumb in the cellular sphere is, at least from my point of view, something like minus 45 dBm. That would be an ultra strong receive signal that happens if your phone is like in a commercial GSM network, if your phone is located very close to the base station antenna. So that's something that can happen in reality. And at any base station, at least. I'm not sure about SDR equipment, but I would expect the same. But at least a commercial base station should be able to deal with that kind of signal level. So if we look at that and we look at the equation that way, then it means we have a transmitter at plus 20 dBm. Where did I get the 43 here? There is a typo in there. It's 45. So between plus 20 and minus 45, there is a total interval of 65. And if we subtract these losses and margin and so on, we end up with something like 55 dBm. So we should not operate, in this example, the UE and the base station with less than 55 or better 65 dB of attenuation, and we should also not operate it with more than 120 dB because then they won't see each other anymore. So that gives us sort of the range of permitted attenuation values between the two devices in question in the uplink direction. Now for the downlink, we need to do the exact same computation. Depending on the sensitivity and the transmit power, the values might be different. So for example, if I use a commercial macro base station, which has a transmit power of 40 watts or something like that, of course, then we are in the if we look back at the, sorry, at that slide, yeah, let's say, yeah, 40 watts would be 49 dBm. As the slide here says 46 is 20 watts, 3 dB more is twice the amount, so it would be 49 dBm. So in that case, basically the downlink signal level at the transmitter would be 49 versus 20 would be 29 dB higher than in the uplink direction, meaning we need additional attenuation in the downlink direction to compensate for that. To make sure that we fulfill the requirement in both ways. The sensitivity will, of course, also be different in the UE versus the base station. The base station typically is better than the UE, but not so like that. That might be like 5, 6, 7, 8 dB difference, but not the 29 dB that we may have just because there's such a strong power amplifier in the macro base station. So, yeah, never mind. Okay, so yeah, one interesting question is, of course, how to get user equipment with antenna connectors. If we use phones, I mean, in the initial example, it was an SDR, where, for example, with SRS UE, since we have some SRS people here, then of course it's easy because we have separate connections. But in in old days, if you look at phones from the 1990s or even until 2005 or sometimes until 2010, you could find phones that had antenna connectors. Those days are gone. So basically, you can't use unmodified modern smartphones in such a wired setup if you really want to have a wired setup. I mean, yes, you can use a shielded box and put the phone in there, but then you don't have a guaranteed defined absolute signal level anymore, and you basically you don't have the kind of wired setup with guaranteed signal levels that we're looking for. The solutions that you have, well, on the one hand side, you can use cellular modems, which are built for, let's say, use in cellular routers, or built for putting them in laptop computers, where usually they have traditionally U.FL connectors, these days mostly MHF4 connectors, so very tiny coaxial connectors. You can use such a modem on a carrier board, in some embedded PC or in some way, and then use that modem driven by AT commands or QMI or other things from an embedded system as a user equipment, and you will have the coaxial connectors on those. You can use an SDR, as already mentioned, or it's also possible to rework if you are, how can I say, willing and able to take apart a modern smartphone. You may find a place where you can actually solder something like an MHF4 socket on the circuit board and then use a wired connection to that. But then you may end up with impedance mismatches and so on. So it's not really a nice solution. So I think the SDR or the cellular modem with coaxial connection are the two solutions to that problem. So I've been talking a lot about attenuation. And how do we achieve attenuation? Well, using attenuators. And what kind of attenuators are there? Well, the simplest form is a fixed attenuator. The picture here shows a product from Mini Circuits with 30 dB attenuation, as it states, also 50 ohms. So it's good from that point of view. So you can buy those in all kinds of values, from 1 dB to 10 dB to 20, 30 dBs, 40 dBs, whatnot. And you can also connect them to each other. They have a SMA male connector on the one hand side, and an SMA male over here, SMA female on the other end. So you can daisy chain them and create whatever attenuation value that you would like to achieve. And basically plug them together. Yeah. The other option is to use rotary switched attenuators. I didn't put a picture here. It's a bulky device with large mechanical switch and lots of resistors built in, and you can adjust a dial in steps. For example, 10 dB steps in this example. So you can dial the dial to 0, 10, 20, 30, 40, 50, 60, 70 dB. The other option is digital step attenuators. These are basically electronic. So all of the devices up to the rotary are completely passive. They don't need supply power. They're pure passive parts, RF in, RF out. The digital step attenuators then need power supply, and you have some kind of digital interface, such as a serial port or parallel pins, and you can then adjust, like with digital control signals, you can adjust the attenuation that they achieve. One thing to keep in mind, maybe, I'm not sure if I have this on a slide, but before I forget about it, one thing to keep in mind is also the power rating of the attenuator. Yes, it's actually here on the second line. Yeah, consider the maximum RF power level and supported frequency band. So if you choose an attenuator, make sure that your actual frequencies are within the supported frequency band, and make sure that your RF signal at the location where you put the attenuator is not stronger than the maximum power rating. So for example, this VAT 30 plus, I don't know for sure, but I would guess it's somewhere between, I don't know, I would say half a watt or something is probably likely its capability. I would have to check the data sheet, but just from looking at it, it's not really something that can carry a lot of RF power, so you cannot connect that to a 10 or 20 watt base station transmitter. It will basically start to glow, and some smoke will come out of it. So you need an attenuator that can handle the power that you apply to it. On the other hand, if you use this device attached to a user equipment, you should generally be fine. Even if the user equipment could, in theory, transmit 2 watts, let's say a GSM phone. A GSM phone will only transmit at 1/8 of the time. So on average, your transmit power will be only 1/8 of 2 watts. So it shouldn't be problematic, even if it's only rated for half a watt. The other topic to look at is sort of to always keep in mind the real world is not as it's stated on the data sheet. So the attenuation values given here in the computations and also in data sheets of products are idealized values, and the real world attenuation will always be slightly different. On the one hand, because the attenuation always depends on the frequency. Typically, higher frequency means higher attenuation. So if you look at the data sheets, you will actually see frequency plots that will show you on the x-axis the frequency, and on the y-axis the attenuation level, and that will change over frequency. All the components have tolerances, and then also you have attenuations in connectors and in every meter of cable and so on. So any real-world setup will likely have more attenuation than what you did in your computations beforehand. Keep that in mind. It will not be drastically different, but 1, 2, 3 dBs is certainly not unheard of. Maybe a bit more even in terms of differences. Yeah, so some more terminology before we look at various devices, components. Something that you always read in data sheets is the so-called insertion loss. And that basically means the amount of attenuation that happens as a signal traverses from input to output. So if you think of the attenuator here, the simple attenuator with 2 connectors and specified as 30 dB attenuator, it will, if you apply a signal on the left-hand side, this signal will suffer an insertion loss of 30 dB, because on the output you will have a 30 dB lower signal. So that's how you can explain the insertion loss. Another term is isolation, which we will get to. That means the attenuation between 2 ports of a multi-port device, such as a duplexer or a splitter combiner, where you have multiple ports, and the isolation defines the attenuation between 2 such ports. Another term you will find in every data sheet is the return loss. That's sort of how much your reflected signal. So there's always some kind of impurities or some kind of imperfections in the device, meaning that not all of the power that you send to it will go through it. A tiny amount will always be reflected back to you, and the return loss now tells you the attenuation of how much of your signal that you're sending to the device is getting reflected back. So if it has a return loss of 20 dB, you send a signal to it of, let's say, 20 dBm, and 20 minus 20 is 0, so you get 0 dBm, meaning 1 milliwatt reflected back from the device. Usually you don't need to care much about this unless you're dealing with very high power levels, where the reflected power can still be a significant amount of money. Not money, power, RF. Yeah, another term is to think of duplex or simplex that occurs in such setups. So base stations typically have separate RX and TX connectors, and that is considered simplex. And it means that also the reason for this is that uplink and downlink need to be isolated, not isolated in a sense that you need to put some isolation tape or something around it, but from the RF point of view, you must not feed too much of the transmit signal back into the receive port, as the base station could be basically deafened or desensitized by receiving too much of its own transmitted signals. This is why there are devices that you can connect called duplexers, which we will get to in the next slides. On the user equipment, we typically have a combined RX and TX connector. Even user equipment that has multiple connectors, such as 4G, 5G modems, those additional ports are for MIMO use and not for RX-TX separation. So if you have 2 or 3 or 4 connectors, those are typically all receive and transmit, and just for multiple, for special diversity, multiple input, multiple output. So for the purpose of interconnecting such a typical base station with a typical UE, we somehow need to split the signal from the UE to the base station, and combine the signal in the other direction, right? Because one device has 2 ports, the other one has 1 port. How do we interconnect those? And that is where normally in cellular networks, a cavity duplexer comes into place, which uses a property of the system that is its frequency division duplex, meaning that the uplink frequency is separated from the downlink frequency in the frequency domain. So there is a different frequency range used for transmit than for receive of uplink or downlink. And this difference in frequency can be used to insert so-called bandpass filters. A bandpass filter basically passes only a certain band, which is the intended band of frequencies, and it rejects all other frequencies that are not part of the band. So basically, a typical duplexer for cellular systems consists of 2 band passes. One is a band pass for the uplink band, and that's connected to 1 port, and the other one is a band pass for the downlink band, and that's connected to another port. And both of these filters are connected to 1 joint port, which is where the antenna is connected. So in a typical setup, you have 1 antenna and connected to the combined port, and then you have a band pass for the uplink and for the downlink frequency band, and those go to the receiver and transmitter of the base station. And you can do the same on the user equipment side if you want to split those combined single connector devices up to multiple ports again. The cavity duplexers are for a fixed frequency band, so you cannot use them in a multi-band approach. So if you want to build a test setup that always tests in 1 single frequency band, you are able to use such duplexers. But if you need something that's agile frequency-wise or operates in multiple bands, then you cannot use a duplexer because the single band device. You have to come up with a more complex solution or work with splitter combiners. There will be a separate slide about this. Okay, the other drop that we have, so far we've been talking about having a single signal and an attenuator with 1 input and 1 output. That's all nice if we want to connect 1 user equipment to 1 base station. And we've spoken about the duplexer to combine or split the receive and transmit signals. We still don't know how to connect multiple base stations to 1 user equipment or multiple user equipment to 1 base station. And if you want to do that, you need so-called splitter combiners. They're always called splitter combiners because, well, basically in one direction it splits, in the other direction it combines, and it's always the same device. The typical characteristics of such a device, and we will look at several of them in the next couple of slides. One of it is the frequency passband, meaning which frequencies you can use it with. The isolation between multiple tributary ports, that's relevant if you use it particularly in the transmit direction. So you have multiple transmitters going into a combiner. Then transmitter A sends some signal into the combiner. and most of that signal goes to the sum port where both of the signals are combined, but a little bit of the signal also goes to the port where the other transmitter is connected. And the isolation defines again how much attenuation there is between those two ports. The insertion loss tells you how much there is a loss between a tributary port and the sum port. So like we had in the, let me just go a couple of here. This is a splitter combiner picture here. So we have, it's just a 2-to-1 splitter combiner. This is the sum port here. These are what I call tributary ports. So the insertion loss is between 1 and S or between 2 and S. That's basically how much of the signal is attenuated while it passes through. And the isolation is between 1 and 2 or 2 and 1, how much those ports are isolated from each other, right? The insertion loss you want to have as low as possible, and the isolation between 1 and 2 you want to have as high as possible. So yeah, also be careful when reading data sheets, and we will look at that again briefly. The insertion loss is often specified as the excess above the theoretical insertion loss. So you have to be careful when looking at data sheets. A 1-to-2 splitter combiner, by definition, splits the power in half, meaning that if you put 10 dBm in, even the ideal splitter combiner, you put 10 dBm in on one on the sum port, and you split it in two, then there will be 3 dB less on both of the tributary ports. So 10 dBm in, 7 dBm out on both of those tributary ports. That's like the theoretical loss. Of course, half of your power is lost in there. And then you have the excess loss that is basically how well the real implementation, how much more attenuation the real world implementation creates on top of the theoretical loss that you have anyway in such a splitter. Look at that. There's also symmetry, unless you really have, I skip that for now. It's goes too far. Yeah, Manaborn reports there's some high quality cheapo splitters. Yeah, with unrealistic data sheets, where basically if you look at the data sheet, you can already tell it's impossible physically to create such a device, because more energy is leaving it than you put in. That's in a passive device. That's obviously not possible. Okay, so we've been talking about splitting, but for combining, it's the same. We use the same device, just in the opposite direction. This way, we can combine multiple signals in there. So all of those signals are bidirectional. The duplexer is bidirectional. Attenuators, splitter combiners are bidirectional. So there is no difference here. So there's a couple of different types of splitter combiners. This first one is a resistive splitter combiner. That's the easiest you can do. Resistive means it is constructed only from resistors internally. And resistors, of course, well, what do resistors do? They convert electrical energy into thermal energy, and therefore they have losses. So the resistor network that's built in such a device makes sure that all ports see a 50 ohms impedance, which is basically, we're talking about 50 ohm systems here. The advantage of the resistive splitter combiner is that it has a high bandwidth, because the resistors are normally not very frequency dependent. So you can use them from basically 0 hertz to gigahertz frequencies. There's a bit of parasitic capacitance inductance in those parts. And yes, there is some frequency dependency, but it doesn't have a strict narrow band like other types of splitter combiners. So yeah, the positive side is it has a high bandwidth, but the negative side is that it has twice the theoretical loss. So if we talk about a 1-to-2 splitter, as I said, there's a 3 dB theoretical loss, of course, and then you have the additional excess, and in this case, it's at least twice. So we are losing 6 dB of our signal for splitting it in two, which is a lot. And it also has the worst isolation between tributary ports, because it really doesn't differentiate between tributary and sum ports. So the isolation is not better than your insertion loss, which, depending on the use case, is not very useful. But it's very cheap and very simple to build and has a high bandwidth. The alternative here is a connectorized reactive splitter. Reactive means it is built from capacitances and inductivities internally. Not as simple to build, at least at gigahertz frequencies. You can buy those ready-made from various suppliers. Here again, an example from mini circuits. I don't get any kickbacks from them. The disadvantage is they have a lower bandwidth. So here, for example, this is already a rather high bandwidth device because it covers 1.5 gigahertz, so from 0.5 to 2 gigahertz of frequency band. Often it's even less. So we use some that only have whatever 800 megahertz to 2 gigahertz or something like that. The advantage is you get much lower insertion loss and higher isolation at higher cost. So it depends on your use case. I just wanted to present the differences between those. And now let's look a bit at data sheets. So this is the same device on the picture here that we saw. No, anyway, doesn't matter. It's again a 1x2 splitter combiner. Here we see frequency range 700 to 200 to 2000 megahertz. So we can use it in all of the GSM bands, 850, 900, 1800, 1900, but we could not use it in the whatever 2.1 gigahertz band for 3G and 4G, and not in 2.6 gigahertz or anything higher than that. It has 50 ohms. That is what we want. We also see the 10 watt maximum RF power input. So all of these things make sense now, given the previous discussions. What we have to look at is now, for example, the insertion loss. Here we see insertion loss above 3 dB. That's what I'm saying. So you see the insertion loss is 0.3 or 0.7 to 0.7 dB, but above the 3 dB. So it means the total insertion loss actually is 3.3 to 3.7 dB between either of those two tributary port and the sum port. Phase imbalance, we don't care. Amplitude imbalance, we also don't care. Let's look at the next. It's also from the same data sheet. Here we have some frequency plots. So we see the total loss here, so the 3 dB plus the point whatever, over the frequency that it covers. So we see, as in most devices, the loss increases as the frequency increases. We also have here both ports, some port to port 1 and some port to port 2, and we see there is an asymmetry between those two ports. It's not 100% symmetric. And here we have the isolation plot. Again, isolation is the unwanted signal from port 1 to port 2. How much is that attenuated? And we see here, well, it's about whatever, 23.5 to 33 dB. And it can go quite different depending on the exact frequency that you pass through these devices. So that's why I'm saying always look at the plots and not just use the value from the table or from the headline of the device. Okay, now we've talked about a lot of different components. One part we didn't cover yet is coaxial cabling. Well, what kind of parameters do we have in terms of cabling? Well, connectors, obviously, you need matching connectors. SMA is the standard in most of the kind of setups I work in. If you go for actual like high power cellular base stations, you will have a 716 connector and you will need adapters for those. Occasionally, you also find N-type connectors or the small U.FL, IP, no, what was it? IPX4, I think. Anyway, the smaller connectors. The cable loss is typically frequency dependent and given and specified in decibels per meter or per 100 meters to be more precise. But the loss is typically relevant in wire test setups where we only have, up to maybe 1 or 2 meters or 3 meters of cable. That loss is insignificant compared to all the other losses that we have in our system. What's more relevant is the so-called screening efficiency, which is also given in decibels. And the screening efficiency now tells you how much of your wanted signal inside the cable leaks to the outside world and vice versa. How much of the outside world, the radio signals on the air get transmitted injected into your cable. So in such test setups, usually you don't want that at all. You don't want your test setup to radiate to the air, into the open space, and you don't want to receive commercial networks in your test setup. So it is always advisable to use cables with high screening efficiency. That means more than 100. There's also cables with more than 110 or even more dB of screening efficiency. And what that means, let's assume it is 100 dB. It means that, let's say you transmit with a signal of, let's say, plus 20 dBm in this coaxial cable. And now you subtract the 100 dB from that 20. So it means that you are at minus 80 dBm. And that is basically what is visible outside of the shielding of the cable in the air. And minus 80, let's take that example, is still strong enough for a phone to see that signal. Of course, it will decrease significantly as you get further and further away from the cable. But even with such a cable, even at 110 or more dB of screening efficiency, if you put a receiver directly on top or within a few centimeters of the cable, you will always still see the signal that's in the cable due to these physical properties. So the cables that achieve that screening efficiency are, the lowest cost ones are rigid flex cables, RJ402 or 405 type. Rigid flex means, well, they are rather rigid. So you bend them once into place, and you shouldn't bend them too often. Not very comfortable to work with mechanically, but rather good in preventing leakage. You can also buy super expensive cables such as Sucoflex, which are more flexible at the same screening efficiency, but then we're talking about really expensive cables, which I typically avoid. I'd rather go for the cheap rigid flex ones. So now let's look at an example putting all of these things together. We have a user equipment here on the left-hand side. We have two base stations on the right-hand side, and we have multiple different elements in between to interconnect those. So first of all, we have some attenuation after the user equipment. In this case, it's two attenuators in series of 30 dB each, meaning we have 60 dB total attenuation here at this point. Meaning, let's say the user equipment transmits at 20 dBm. We subtract the 60 from that. So it means at this point here, we have minus 40 dBm as the highest possible signal level. Then we go through a 1x2 splitter combiner because we want to be able to talk to two different base stations. Now that splitter combiner has, if we use the one from the previous data sheet, it has about 3.5 dB of insertion loss. So we had 40 dB here. Let's say it's 4 dB for the ease of doing the math in my aging head. So but we said we had, minus 40 dB here. So 4 more dBs, minus 44 dB at this point, left and right here. Then we have a duplexer. The duplexer is required because the base station has separate transmit and receive ports. The duplexer has, let's say, 1 dB additional loss. So we're at minus 45 dBm at this point and at this point. And that is what we get into the base station here, which is a very strong signal still. So we could put more attenuation here, but we could definitely not put less attenuation in this setup to make sure that we don't overdrive the base station receiver here in the uplink direction. If we do the same for the downlink direction, we will see it's basically the same because all of those parts are symmetric. So we again have the same attenuation, but we have an additional attenuator here only in the downlink transmit. And sorry for those errors here, actually are the wrong way. But yeah, that's how directed graphs in GraphWiz work. I couldn't be bothered to use different tooling here. So of course, the downlink signal goes from right to left, opposite to all of these arrows here. But there's an additional 20 dB in the downlink to accommodate for the fact that this base station has a stronger transmitter than the user equipment has here. So let's assume the base station would be transmitting at whatever 30 dB for 30 dBm, for example. That's 1 watt. We have an additional 20 dB in here. So the receive level over here would be, what was it? What did we compute here? Was it minus 45 or something like that, if I calculate correctly in this direction? So again, adding up all the attenuations, let's compute that. That's easier this way. So we have 30 plus 30 is 60, plus 4 is 64, plus 1 is 65, plus 20 is 85. So we have 85 dB between the transmit port and the UE port here, assuming we transmit at, what did I say, at 30 dBm plus, of course. We subtract the 85. So now that is the signal level that, so it's 55, if I'm not mistaken, minus 55 dBm over here as a receive level. And the same applies. This is completely symmetric here. So this is just a copy and paste of the upper block. And if you have more base stations, of course, you can just use a 1x4 splitter combiner here and put 4 of those blocks. Of course, the 1x4 splitter combiner will have an additional 3 dB of loss because it again divided the signal not by 2 but by 4. So you have 3 dB more in the entire chain. But apart from that, it will be all the same. And this, yeah, IPEX4, is it in the M2 cards? I think it's MHF4. That's the name I know it from. Now I recalled it again. Manawurm just mentioned this. So the connector, I know it as MHF4. In any case, so yeah, this kind of setup, as it says here, is basically for mobility or handover testing. So we have a single UE and that has 2 base stations. And now we can, do handover mobility between those 2. If we really want to automatize such a setup and we cannot adjust the dynamically the transmit power here or artificially the receive level here, we could add a digital step attenuator or a rotary step attenuator in this path here or in this path here or even here or here. And then we can basically make one cell level lower than the other cell, and at that point then once the hysteresis values and whatever is configured for cell reselection would make the change between those 2 cells. And I can also see the measurement reports as they adjust and so on. So that's an example in that direction. This is another example in the other direction. So here we have 4 UEs and 1 base station. In this case, let's say we just want to do functional testing, making calls or exchanging data or whatever between multiple UEs connected to 1 base station. So in this case, the setup looks slightly different. This block here, the base station plus the additional attenuation for downlink and the duplexer is exactly the same as in the other side in the previous diagram, just that we only have 1 of these. But on the user equipment side, it looks completely different than before. So on the previous slide, we just had a user equipment going into attenuators, going into the splitter. But now we have multiple user equipments and we are faced with the task of somehow connecting them, combining them into 1 signal. And the only way to do this is by first going through a significant amount of attenuation and then go into a splitter combiner with reasonable isolation properties. Why is that? Because we always need to think of this UE transmitting, going into the splitter combiner, and then suffering the attenuation of the isolation and going back to the previous UE. So if we just took, let's say, 2 GSM user equipment here, did not add the attenuator to it, and went into a splitter combiner that maybe only has whatever 6, 7, 8 dB of isolation between those 2 ports, then you transmit here in the worst case at plus 33 dBm. You only suffer through 6 dB of isolation loss over here, meaning that you get 27 dBm of signal back into the user equipment. And that's certainly something that the receiver in this user equipment will not like at all. because that's not what it's designed for. It is expecting a much weaker signal at a much lower level. And it will certainly, if you do that for a long time, for sure, it will die. And to solve this problem, we basically need to increase the isolation between those two. And we do that by putting attenuators here directly in line with each user equipment. So a signal that gets transmitted here is, let's say, plus, again, use the example of plus 33 dBm. It gets attenuated by 30 dB, so we only have plus 3 dBm. It goes through the splitter. Let's assume, for the sake of the example, this only has 6 dB of isolation. So it means we have minus 3 dBm here. And then we go through another 30 dB attenuation. So we are at minus 33 dBm. So whatever the UE on the top transmits arrives at minus 33 dBm down here, and that's already a much more reasonable signal level to arrive. Still a lot, but much more reasonable than the previous example if we didn't have those attenuators here. Also, if we use not a resistive splitter combiner, but a more expensive reactive splitter combiner, we could easily have 20 or more dB here, again increasing the isolation and making this a bit more relaxed. So depending on which part you choose here, you can adjust your values over here. But this is the 30 dB is the safe approach, let's say. So that's the isolation concern between multiple UEs. Now looking through the entire path between E node B and UE. So we see here we have the UE, we go through 30 dB. So 30 dB, we have this 1x4 splitter combiner. Let's assume it is a resistive splitter combiner, which has, so the theoretical minimum split in a 1-to-4 splitter combiner is about 1/4 of the signal. So meaning that we have 6 dB theoretical loss. And in a real-world implementation of a resistive splitter combiner, we have at least twice that. So we have 12 dB insertion loss, let's say, here. So 30 dB plus 12 is 42 dB, plus another 30 is 72 dB of attenuation. Then we go through the duplexer, who has 1 more dB. So we have 72 dB uplink attenuation here. And in the downlink, we again have the additional 20 dB, so 92 dBs in the downlink direction of attenuation here in the signal. So that's it for this example. And now you can, of course, build more complex constructs with more splitter combiners and have multiple base stations and multiple user equipment, or you can add a hierarchy. So you can first have a 1x4 splitter here and then a 1x8 splitter here and 8 UEs. So you can basically grow from those simple examples into more complex RF distribution networks. Just always have to look at what is the attenuation between for the uplink, what's the attenuation for the downlink. Do those values make sense? Do I have proper isolation between neighboring UEs? And do all my parts, are they able to sustain the RF power level that they are exposed to? On the user equipment side, it's typically not a concern, but here, this 20 dB attenuator, if this really is an E node B that can transmit at whatever, let's say, even only 10 watts or 20 watts or whatever, you need a rather high-end beefy attenuator that has a large heat sink, so it can actually handle that RF power that it is exposed to here. And that's it. That's really all that is to it, to designing such a RF distribution network and putting it together. So maybe take a quick, or not so quick, stop here before I go on to some more advanced topics, in case somebody has questions about what I covered so far in the time so far. Okay, everybody's asleep by now. Nicely done. Okay, NP-comp is typing. So let's wait for some questions to arrive. Meanwhile, I can have another sip. Yeah. Okay. Well, if there are no questions so far, or people already forgot about the questions, then I move on with the next slide. Yeah, so now we can build those kind of setups. So what about MIMO? All this legacy 2G stuff, nice and fine, but what about LTE, where it's not single in, well, or at least not only single in, single out, but multiple in, multiple out, typically 2x2 MIMO. Well, you can treat each of those RF paths separately using the same principles and paths. So instead of just building one downlink and one uplink, you build basically two uplink and two downlink signals and have separate attenuators and so on. In this case, you really have separate paths, and you for sure have a lot of separation between your not sure MIMO planes or whatever you might call them. Better than in any real in any real world radio link where the individual paths are never separated by such an amount of isolation like in such a setup. But you can do that. There is a, I thought it was linked here, but the hyperlink is somehow gone. But yeah, my company Osmocom, we did a device called RFDSAT, which is a digital step attenuator with 4 channels exactly for that purpose. So you can have 2 uplink, 2 downlink channels for a 2x2 MIMO use case and adjust the attenuation in that. Another option you have, especially in larger setups, if you really build this, let's say with many dozens of user equipments or even hundreds, you get at a point where you need a certain amount of attenuation on the one hand side to guarantee the isolation requirements, for example here, or also if you have multiple base stations, you also have to think of isolation between those base stations. So you need a certain minimum attenuation for isolation requirements, but then overall you might get in trouble with your link budget if this network grows. So if you have like 2-3 layers of splitter combiners, you cannot have this attenuator in here in anymore, and you basically get constrained by the amount of loss you can sustain in your system. But one option, of course, is to use RF switches if you don't need all of those connected concurrently. So it depends on your test setup and what you want to do. But there are RF switches, not just single pole dual throw SPDT switches, but also higher order like SP60 or whatever. So you can basically select 1 out of 6 signals in that example. The classic way to do it is to use coaxial relays, very expensive devices, but can carry a lot of power. The more high-tech modern way to do this is use MEMS switches. That's micro electromechanical systems. So basically, it's just a chip component that has a switch built in, but those cannot carry significant RF power, but have a much lower cost. So the advantage of the switch is it has a very low insertion loss, whereas if you have a splitter, that insertion loss goes up a lot because all of the components are connected at the same time. So that's an option you can do. So if we look at the base station side, you may remember that earlier on I said, well, using the duplexer here as a frequency-dependent part means your base station is restricted to a single band. You can do that also with a splitter combiner. Depending on the amount, depending on some parameters. So the duplexer has the nice property that between RX and TX, you typically have something like 80 dB of isolation, meaning that whatever you transmit here, even at ridiculously high power on the transmit side, will not end up at the RX side. Remember, this duplexer is designed for a system where you don't have an attenuator here. In a normal base station deployment, you have your base station. That base station might transmit up to 40 watts of power. That goes into the duplexer. And of course, it's not attenuated beforehand. Here you have the antenna on the left-hand side. And the isolation between the transmit and the receive side is sufficiently high that you don't desensitize or even damage your receiver of the base station. So that's really nice for real-world deployments, very low insertion loss and very high isolation, but it's specific to one band. And if you need a setup where you can cover multiple different bands with your base station, then or adjust the frequency or the band of your base station for different test cases, you can do that with a splitter combiner here, provided that you have sufficient attenuation here and the splitter combiner has sufficient isolation built in here. So if you have a nice you cannot use resistive combiners. If you have a nice reactive splitter combiner here, then it has something like 20 to 30 dB of isolation here, plus the attenuation you put in here. Maybe you make that even a bit higher, put 30 dBs here and you have 30 dB here, so you have 60 dB of isolation like between those 2 points, and that is already sufficient again. TNT mentions whether I ever used circulators. Not really. I've seen circulators used but they are again very frequency dependent, so they don't help you in this case. So yes, you can use circulators in such a setup. I've mostly seen circulators as protection devices for RF power amplifiers, so that if you don't have an antenna and all the RF power gets reflected back, you don't kill your RF transmitter, but it goes into a resistor. But at least those circulators that I'm familiar with, they are even more frequency dependent than duplexes. So they have a very narrow frequency range. So it doesn't really solve the problem for a wideband system. I'm not sure if there are other circulators, but at least those that I know are highly frequency band dependent. Yeah, so yeah, you have less isolation, but if you put this additional attenuation here, or maybe even in the receive path, depending on your overall link budget, you can basically get an as good isolation from the base station point of view by this additional attenuation elements, and you can use a splitter combiner, which has a wider frequency range than your approach with a cavity duplexer here. One other option you have, I mentioned it earlier, is you can also simulate RF delay. In TDMA systems like GSM or LTE, there is something called a timing advance to compensate for signal propagation delay between the user equipment and the base station. Simulating that with actual coaxial wire, with kilometers of actual coaxial wire, is highly unrealistic. So the way to do this really is to use an RF delay simulator, which basically is an SDR receiver and transmitter with some memory to buffer samples in between. And TNT here on the call did the Osmo RFDS project a couple of years ago, which does exactly that with a Pluto SDR. So you can hook that into such a setup, and then you can simulate delays and verify, for example, whether your timing advance loop in your implementation of the UE or the base station side works as expected. Another option is to simulate entire RF channels. RF channel models are mathematical models that try to approximate real-world propagation in certain conditions, rural, urban, dense urban, moving vehicles at certain speeds, and so on. And they simulate not just the attenuation that you could do with an with a step attenuator, and not just the delay like the Osmo RFDS, but also multipath fading, Doppler shift, and other effects. And yeah, you can just put a simulator at any point in such a network, always keeping in mind the input and output RF power levels, and then have such simulation capability in such a wired test setup. And that brings us to the end of the slide set. Yeah, I did want to put some links here, but in the end didn't find the time to do so. My apologies for that. Struggled too much with the new slide system. Okay. With that, that was what I wanted to cover. But yeah, if there are questions, I'm very happy to answer them or look at some data sheets or whatever. So since there are no questions so far, let me get back to one device that I had shown here. The example picture that I actually had for a resistive splitter combiner, that's actually not entirely true, because that's the resistive splitter combiner is those 5 resistors here in the center. If you see those 5 sort of light brownish things in the center, that's the resistive splitter combiner. And these larger black parts here are attenuators. So it's actually a combination of, if we look at this setup, it's like the device that you saw on that picture is actually the 1x4 splitter combiner in a resistive way, plus those 4 attenuators here, plus the attenuator here. That's all on a single circuit board. And with 4 UFL connectors, so you can easily connect cellular modems to it, and 1 SMA connector, so you can easily go to a base station. So that's a board that we did at Sysmocom some time ago, exactly for such test setups. So we don't have to buy, 5 expensive mini circuits attenuators for, I don't know, 15 or 20 euros each. Plus then all the adapters and whatnot, and the splitter combiner, and just put all of that on a board. It's was an easy way. So that, just as a side note. Yeah, so TNT mentions that yes, circulators would be very frequency dependent, but one could use them if one were to try to extend it to a TDD system. Yes, as I said, I didn't cover TDD here. It has completely different requirements. I don't have any personal experience with TDD, so I didn't want to speculate about it. Maybe also, like, if you actually build something like that, I didn't say anything about measurement. So the most useful tool to have is an RF power meter, of course, in such a setup, or a spectrum analyzer, or both, so you can actually see what kind of signal levels you're getting. What's also very useful to have is a network analyzer. Doesn't have to be a vector network analyzer here. In this case, it could even be a scalar network analyzer. That's basically a device that you can attach any kind of RF distribution network to, and it will plot you the attenuation, not just, but as a minimum, it will plot you the attenuation over the frequency. So basically, the kind of plot that you saw here with loss over frequency, that is something you can generate automatically on the screen with the network analyzer, and not just for a single device, but for your entire network. So you could basically attach one port here and another port, I don't know, somewhere here, and with no UE and base stations and so on connected, and you get like your total attenuation over the entire network, over a configurable frequency band, and you basically can measure whether it does what it's supposed to do. But of course, network analyzers are rather expensive, so maybe not available for everyone. Just saying that's sort of the kind of things you can do. And in absence of a network analyzer, what you can do is you can attach some signal generator. It could even be an SDR that generates a signal if you have an SDR lying around. And then you test what kind of signal level is present at any of these ports over here with another SDR or with a spectrum analyzer or something like that. Yeah. Manabum says there's cheap Chinese VNAs. Unfortunately, I think they're, at least those that I'm aware of, are rather restricted in frequency range. So basically, yes, for like, I don't know, 70 centimeter or 2 meter amateur radio, but not really for cellular systems where you would need to cover at least up to 2 gigahertz. But maybe I'm not up to date with the latest and greatest in Chinese VNAs. Okay. So up to 3 gigahertz. Okay, fine. Then that I'm not up to date.